Hello everyone, welcome to Amban 109. And for today's video, we're going to review about quadric surfaces. Given an equation in the form ax squared plus by squared plus cz squared plus dx plus ey plus fz plus g equals 0, where all the coefficients a to g are real numbers, and at least one of the coefficients of the squared terms a, b, or c is non-zero, graphing this equation results in what is called a quadric surface. Quadric surfaces are just 3D analogs of the conic sections. There are in total 6 quadric surfaces. So let's start with number 1, which is the ellipsoid. So the ellipsoid is a quadric surface with an equation for the form shown. You have x squared over a squared plus y squared over b squared plus z squared over c squared. So as you can see, all of the squared terms are positive. So the ellipsoid, we can remember that as all. All squared terms are positive, and all of its traces are ellipses. So there are special cases for the ellipsoid. First is that when all of the coefficients are equal, a, b, and c, then we have a sphere. Next is when exactly two are equal, let's say a and b, but the third one, c, is not, then we can categorize it further into two. So first is when c, or the third coefficient, is greater than the other two, then we have the prolate spheroid. Next is when the third coefficient is less than the other two, then we have an oblate spheroid. So the prolate spheroid is generated when an ellipse is rotated about its major axis, while the oblate spheroid, you guess it right, is when it is rotated about its minor axis. So that would be it for the ellipsoid. Second on the line is the elliptic hyperboloid of one sheet. So it is a quadric surface with an equation of one of these forms right here. As you can see, there is still equal to 1 on the right-hand side of the equation. And this time, there is exactly one negative squared variable or negative squared term. So it is in the name itself, elliptic hyperboloid of one sheet. As you can see, there is a continuation here. There is no gaps. Looking forward here, in the graph shown, it is the manifestation of the first equation here. At the xy plane, or when z equals 0, it traces an ellipse. And parallel to that plane also traces an ellipse. It is because it is the negative variable here. While the other squared variable, which are positive, actually traces the hyperbola, making this elliptic hyperboloid of one sheet. If there is elliptic hyperboloid of one sheet, there is also the elliptic hyperboloid of two sheets. So you can see there is a gap right here, right now. So here in the graph, it is the manifestation of the first equation here. All of these forms of the equation have exactly two negative squared variables on its equation. So here, the positive squared variable is the x-axis, or the x variable. As you can see, there is a gap on the x-axis, but further down in line, it traces an ellipse, while the other two squared variables actually traces a hyperbola, making it elliptic hyperboloid of two sheets. Fourth would be the elliptic cone. So the elliptic cone has equations in these forms. So it is quite similar to the elliptic hyperboloid of one sheet, since it has a negative squared term. It has one negative squared term, but this time the right-hand side of the equation is equal to 0. So this graph shown is actually the third equation right here. As you can see on the z equals 0, or the xy plane here, there is a pair of intersecting lines. So this pair of intersecting lines is actually a degenerate hyperbola. Okay, and there is also on the xz plane right here, and y equals 0. So this y and z equals 0, this is actually the positive squared terms of the equation. While the negative squared terms right here, the x variable actually traces the ellipse, okay? So that would be for the elliptic cone. Fifth is the elliptic paraboloid. So the elliptic paraboloid has a linear term on one side of its equation right here. The given graph is actually the manifestation of the first equation right here. And as you can see, C is not squared this time. And this linear term can either be positive or negative. Here, this is positive, so it is oriented upward, the z-axis, right here. As you can see on the z equals 0 here, it actually traces a point, okay? It is a vertex of the paraboloid or the tip of the paraboloid. So parallel to the xy plane, the plane traces an ellipse, while the other two squared terms, you guess it right, traces the parabola, making it elliptic paraboloid. Lastly is our Pringle chip or the hyperbolic paraboloid. Again, there is still a linear term on one hand side of the equation right here, but there is now a negative squared variable on the equations, any of these forms. Okay, as we look on z equals 0, again, there is a pair of intersecting lines, a degenerate hyperbola, but further down or further up, say parallel to the xy plane at z equals 8, it actually traces a hyperbola. So this graph right here is a manifestation of the first equation, while the other squared terms right here, positive or not, actually traces the paraboloid. So hyperbola plus parabola, we have the hyperbolic paraboloid. So that would be it for our review. So it's time for us to solve some problems. So we are tasked to identify the type of the quadric surface given its equation, identify the coefficients a, b, and c, identify the traces of the surface on the xy, yz, and xz planes, and finally sketch the quadric surface. So I'm going to turn off my video so that we can optimize the space, and that you can grab now your pens and rulers so that we can start graphing. First, we're given the equation 36x squared plus 9/4 y squared plus 9z squared is equal to 9. What is your guess what type of quadric surface it is? Okay, as you can examine, there are square terms here. So we can infer that it must either be an ellipsoid or an elliptic hyperboloid of one or two sheets. We divide both sides of the equations by 9. So we have 36 divided by 9 is 4. 9/4 divided by 9 is 1/4. 9 divided by 9 is 1. As you can see here, we must transform this into x squared over a squared, but we are stuck with 4x squared. So what are we going to do is to find the reciprocal of 4, which is 1/4, and put it below the x squared. We have x squared over 1/4 plus y squared over 4 plus z squared over 1 is equal to 1. So there is a 1 here so that it is more evident, so that we can identify the coefficients a, b, and c. A is just the square root of 1/4, which is 1/2. B is square root of 4, which is 2, and c is just the square root of 1, which is 1. Next is that to identify the equations of the traces on the surfaces. Since it is an ellipsoid, all of the traces are ellipses. So when z equals 0, we can just omit z here. So we have x squared over 1/4 plus y squared over 4 equals 1. When y equals 0, emit y, we have x squared over 1/4 plus z squared over 1 equals 1. And when x equals 0, we have y squared over 4 plus z squared over 1 equals 1. So it's time to graph them out. First, we're going to take note that the coefficients are a equals to 1/2, b equals to 2, and c equal to 1. So these coefficients are just the major and minor axes of the traces of the ellipse. So first, let's set up our coordinate axis. Time to graph the ellipsoid. So we will graph the coefficients. We have a equals 1/2. So this would be our vertices and co-vertices of the ellipse. So we have 1/2 right here and negative 1/2 right here. Next is for b. equals 2. Since it is below y, we have 2 here, and we have negative 2. And for z, we have c equals 1 and c equals negative 1. So first, on the xy plane, we have x squared over 1/4 plus y squared over 4 equals 1. So we're just going to connect these up right here, the coefficients of x and y. Next is for the yz plane, which is y squared over 4 plus z squared over 1 equals 1. Connect the coefficients of y and z. Next is for the xz plane, which is x over 1/4 plus z squared over 1 equals 1. Connect the coefficients of x and z. Okay, I'm very sorry, guys. I'm really not an artist. But as you can see, it is a rough sketch, okay, of the ellipsoid. So we're going to confirm this one by on the next slide. We have this. This is graphed on GeoGebra. As you can see, it is quite accurate. As you can see, this is 1/2 right here. This is 2, negative 1/2, and this is 1. So one quick remark is that it's important to get the intersections on the axis. The edge of the surface must be at the values 1/2 at the x-axis, 2 at the y-axis, and 1 at the z-axis. So these values right here are just the coefficients a, b, and c. Last problem would be this equation right here. What is your guess which type of quadric surface it is? So you examine the equation, there is a linear term z here. So it must be a paraboloid, albeit we don't know if it is elliptic or hyperbolic. We multiply both sides by negative 1. So we have negative z is equal to negative 2 plus x squared plus y squared over 4. Add to both sides of the equations. We have 2 minus z is equal to x squared plus y squared over 4. We make z positive, so we bring out the negative of that. We have negative of z minus 2 is equal to x squared plus y squared over 4. And then put this negative on the denominator, so we get this form right here. As you can see, the squared terms are positive. So this confirms that this is an elliptic paraboloid. And we have c, the denominator of the linear term is negative 1. And since it is less than 0, the paraboloid opens towards the negative z-axis. So the effect of the constant term 2 here is to shift the paraboloid upwards. So this will serve as our guide when sketching the quadric surface. So now we get the equation right here as shown. And then we can identify the coefficients. A is just the square root of 1, which is 1. B is just the square root of 4, which is 2. And C is just the denominator of the linear term, which is negative 1. Next is we can identify the equations of the traces of the surfaces. First is when z equals 0, and then we can get x squared plus 1/4 y squared is equal to 0 minus 2, which is negative 2, all over negative 1, it will become positive 2. And then we divide both sides of the equations by 2, so we have x squared over 2, y squared over 4 divided by 2, which is y squared over 8, and 2 divided by 2 is 1. So we get an ellipse. Next is when y equals 0. Remember that this one right here is just equivalent to 2 minus z, as shown earlier. So we have x squared equal to 2 minus z. Subtract 2 to both sides, we have like that, and multiply negative to both sides, we have 2 minus x squared. So we have z equals 2 minus x squared in the xz plane. And we do the same for x equals 0 or at the yz plane. So we have 1/4 y squared is equal to 2 minus z. Subtract 2 to both sides, you have 1/4 y squared minus 2 is equal to z, negative z. And then multiply both sides by negative 1, we get this one right here, which is z equal to 2 minus 1/4 y squared, which is a parabola. So now we have the equation. This is the original given equation shown. So first, again, let's set up our coordinate axis. remember from the previous slide, we have that on the xy plane, we have x squared all over 2 plus y squared over 8 is equal to 1. So the minor axis is just the square root of the denominator, which is square root of 2, which is approximately 1.4. And then the major axis is the square root of 8 is equal to square root of 4 times 2. We have 2 square root of 2, or it is approximately 2.8. So we graph that here. So if you have a ruler, it would be a more precise representation, but note that this is just a rough sketch. Next is for the square root of 2, we have about 2.8. And since it is an ellipse, we just trace the vertex and the co-vertices. So the xz plane has the equation z is equal to 2 minus x squared. So when x equals 0, we have z is equal to 2. It's just a point here, okay? 2. But when z equals 0, we get this equation, 0 is equal to 2 minus x squared. So we subtract 2 to both sides. You have negative 2 is equal to negative x squared. That would mean x squared is equal to 2. So the solution are positive, negative square root of 2. So we connect this to here and this to here to get our parabola. Next is the YZ plane. So similar to the one we've done before, we have z is equal to 2 minus 1/4 y squared. And when y is equal to 0, again, z is equal to 2. But when z is equal to 0, the equation will be 0 is equal to 2 minus 1/4 y squared. Subtract 2 to both sides. We multiply negative 4 to both sides. We have 8 is equal to y squared, or y squared equal to 8. And y, the solution here is just positive, negative square root of 2. So we will just connect this one right here to this one right here to get our parabola. So all in all, this would be our elliptic paraboloid. So we're gonna confirm on the next slide if this sketch is accurate enough. Okay, so this would be the elliptic paraboloid when sketched on GeoGebra. So a quick remark right here is that the major axis of the xy plane ellipse is the y-axis, where the length is 2 square root of 2, or about 2.8, while the minor axis of the ellipse is, or has a length of square root of 2, which is about 1.4. And the elliptic paraboloid has a tip at z equal to 2. So that would be it. Thank you for watching. So if you have time, sketch the other 4 quadric surfaces. So thank you and good luck.